So dear students, after rolling operation, now we are going to see the drawing processes. Okay, so in the drawing process we are having two operations, that is the wire drawing operation and the tube drawing operation. So let us see the first drawing operation. So basically, what is wire drawing operation? So here, to reduce a given rod into the wire, okay, in the reduction in the diameter for a given rod, it is known as the wire drawing operation. Generally, the rod diameter less than 10 millimeter, we can call it as the wire. So this wire we are going to get from the rod. So the input is rod, and this rod is undergoing deformation through the die. Through the die we are having various zones, and at the end we are getting the wire of required size. So definitely for the deformation of the given rod we are going to use the die. Okay, so the die, which are generally high carbon steel, high speed steel, depending upon the size of the wire we are going to select the material for the die. So of course this die is having the conical portion for the deformation and the straight portion for the sizing of the wire. But of course the main thing is that the deformation is going to happen in the conical portion. So let us see the diagram. So students, see here, this is the die. So see here, this is the die having four main zones. So this is the conical zone, that is, this is for deformation. Okay, this is also the conical section for lubrication. This is only the straight cylindrical portion for the sizing of the wire, and this is the fourth for easy withdrawal of the lubricants. So see here, this is the input as a rod diameter. Say this is a D original as a rod, and at the end we are getting as this final diameter, which is the wire. So here the output is a wire and input is a rod. So this is the die, this is the die. Okay, so how many zones are here? In the wire drawing die we are having four zones. Zone number 1 is the deformation zone. Zone 2 is the lubricating zone. Zone 3 is the sizing zone, and zone number 4 is our converging, sorry, it is a diverging zone. Okay, so this conical angle we are having as 2 alpha, this value is 2 alpha. So this length of deformation zone is nothing but the lie land. Okay, this is the original, this will be the final, and this wire is going to attach to the gripper, which can going to coil this wire onto the power reel. This wire is going to get coiled on the power reel. Okay, so to get this tensile, or we are getting the pull on the wire. Okay, so see here, this is the rod we are passing through this die, conical die, where it is rod getting deformed, and after sizing at the end we are getting the wire. Okay, so there are four zones. This zone is deformation zone, this is lubrication zone, this zone is sizing zone, and fourth one is the lubrications are coming out from this zone number 4, that is the diverging zone. Okay, so here this conical angle of this die, generally I am taking as half the die angle, half the die angle is alpha, okay, which is ranging from 6 degree to 24 degree. Okay, for very soft materials we can having this angle up to say 6 degree, and for the hard material like steels we have having the angle of maximum up to 24 degrees. Now see here, the initial diameter is what? Initial diameter is equal to DO, that is the diameter of rod, and final diameter is nothing but D final. Okay, now from here we can have here the value for K is called as coefficient of elongation. Coefficient of elongation, that is, you can also call it as the draft in the operation, is equal to this A original divided by A final. Okay, what is the draft in the operation or coefficient of elongation? Is A original divided by A final. And what is the percentage reduction in area? In area we can have it as A original minus A final divided by A original into 100. It is in percentage. Okay, so K is the coefficient of elongation. Reduction in area, percentage reduction in area we are getting as original area minus final area divided by original area. Okay, now see, this wire at the end, wire is going to get pulled from the die and it is coiled on the power reels. Okay, so it is always subjected to tension. So the stress which is responsible to get the wire drawn is the tensile force. Please remember the which type of stress is used basically here, the tensile. Okay, now so before the operation of wire drawing we have to do some previous things before the operation, that the rod or the material for the wire drawing should be ductile enough. It should have very good ductility. For that we are generally doing the annealing operation before the main drawing operation for this stock that we are going to use for the drawing operation. So annealing is must. किसके लिए? To get the good ductility in a given material, because the ductility is very important property for the wire drawing operation. Okay, so that is one thing you required here. So if I talk about this deformation zone first, now I'm going to discuss the deformation zone, where the actual deformation going to happen, material is going to yield beyond its yield strength and lesser than its ultimate strength, so that it can deform easily through this conical die. Die angle कितना होता है? For this alpha 6 degree to 24 degree, or 2 alpha is equal to 12 degree to 48 degrees. Okay, and what is this coefficient of elongation? Is equal to original area divided by final area. Percentage reduction, how to calculate we have seen. Now let us talk about this lubricating zone. So see, from the zone 2 we are going to supply the required lubricants into the operation. Okay, now which kinds of lubrication that we can able to use in the wire drawing process? So see, basically there are two lubricants, that is liquid lubricants and solid lubricants. So these are the two lubricants, and the third case is that when we are not going to use at all the lubrication in the wire drawing process. If I talk about the lubrication, in the lubrication I am talking for the lubricants. So there are liquid lubricants, okay, then solid lubricants, and third case we can have with no lubricant. See, the liquid lubricants that we are going to use in the wire drawing operation are, we are having the vegetable oils, we are having SAE oils, then we are having the soap solutions. So these can be the liquid lubricants we can use in the wire drawing process. But see, by using these liquid lubricants in the wire drawing operation, we are going to get a dull surface finish or a dull surface. We are going to get a dull surface. Okay, remember this. When we are using the solid lubricants like the graphite powder or the carbon powder, by using these solid lubricants, we are going to get very bright and shiny silvery appearance on the wire. We are get bright, shiny or silvery appearance on wire. Please remember, very good surface finish that you are going to get onto the wire surface. And of course, with no any lubrication, we will get the black or blackish or burnt surface on the wire. Please remember this. So for lubricants, solid lubricants or no lubricants, what kind of surface you can going to get in the wire drawing operation. Okay, so this is about the lubricants. If I talk about the third zone, that is the sizing zone, you can see here, this is the only zone you can see the straight line, okay, or this is the straight only, otherwise all these are the conical in shapes. Okay, so basically here the sizing zone is provided into this die for converting whatever the elastic deformation or whatever the elastic recovery into the again plastic deformation. So we know that to convert the entire elastic deformation into the plastic deformation, we have to keep the load for a certain amount of time. And that is the thing we are doing here. We are keeping the same load, see, because it's a constant cross sectional area. So, and it is having some amount of length up to 5 meters also, we can have the length of the sizing zone. So the rod or the deformed part is getting some time. In that time, the constant load is get applied on the given rod or material, so that whatever the elastic deformation is present within the plastic deformation, that is nothing but the recovery, elastic recovery, will get again converted into permanent or plastic deformation. So that's why this sizing zone is provided. Okay, so sizing zone is over, and of course zone number 4 is a diverging zone. That's easy removal of wire and easy removal of the lubricants that you have provided from the zone number 2, so that there will not be any splashing of the lubricants, or they should not come with very high pressure. To avoid that, we are using this diverging zone. So these are the 4 zones in the die for use for the wire drawing operation. Now if you look at the speed of the wire drawing operation, so please remember that to draw a very fine size wire, the speed can be goes up to 1800 meter per minute. So very fine wires, if you want to draw, you are having the large speeds up to the 18, maximum speed you can have up to 1800 meter per minute for the large size wire, large sizes, whereas not for large size, you can very fine wires, sorry. Please remember 1800 meter per minute you can go for very small or fine size wires, whereas for the large size wires we can have the speed of 10 meter per minute for large wires, large size wire. So jitna small wire hoga you can go for the highest speeds, but as the diameter goes on increasing, the speed goes on decreasing. So very large wires you can have very small speed up to 10 meter per minute, but for fine wires this is the maximum speed we can go. Now let us talk about the die materials which is going to use in this wire drawing operation. So for very long runs we can have the chilled cast iron dies, but basically the dies used for this wire drawing operation. See, if you are going to have some large size wires in the operation, so to draw these large size wires we are going to use the carbon steel or the high speed steel. High speed steel is used as a die material, whereas if the size of the wire is in the medium range you can go for the tungsten carbide dies, and when you are going for very fine or very small wire sizes, you can use the black diamond dies as a die material. Please remember what are the materials. The die materials for large size wires we can use the carbon steel or high speed steel dies. For medium size wires you can use the tungsten carbide. For fine wires or very small diameter wires or fine sizes you can have the black diamond dies can be used. Okay, so these are the die materials. Now see, one more thing that we have to discuss here. When you talk about this deformation zone, so of course when the drawing is proceeding, so there is a frictional forces that are going to induce, isn't it, at the interface of this die material and this workpiece material. So here always see in wire drawing operation the frictional forces are going to act opposite to the pull of the draw, isn't it? So if we resolve this frictional force, say if the pressure applied by this die onto this workpiece, say Px, then this frictional force will be what? Tau x, which is nothing but mu times Px, where mu is the coefficient of friction between the die and the workpiece. So basically see, these are having two components. One is, of course, this is angle alpha, isn't it? So this will be mu Px cos alpha, and this component of force will be mu Px sin alpha, isn't it? So see, any vertical force onto this die, definitely it is going to damage the material, but opposite to this, when we are using this horizontal component of force, that is the pull, okay, to draw the wire, is always helping for us to get the wire drawn. Okay, so horizontal component of force is always welcome here, but we cannot have this vertical component of force, as it is going to make the failure of this die because of this force, isn't it? So please remember this. Now let us find out the load in the wire drawing operation. The load, or rather you can say the force. So for the force calculation, we have to first find out the drawing stress. The drawing stress. Okay, so for that, in the drawing operation we are having case number 1. When you talk about the ideal case of deformation, that is, during the deformation there will not be any kind of friction will get present in the process. That is the ideal case of deformation. Okay, ideal case of deformation. And the second case is what? By considering the friction and the redundant work in the process. That is the inhomogeneous deformation, or the work which is not utilized entirely into the deformation, that is the redundant work. Okay, so these two conditions we have to consider. From that we are getting the different formulas for the force calculation. So here, if I take the ideal case of deformation, where the drawing stress sigma d, now I am calling it as the drawing stress will be equal to the yield strength of the material into ln of A original by A final. Please remember, sigma y is the yield strength of the material when there is no any kind of strain hardening is going to occur into the material during the working. So directly you can take the yield strength of the material into the strain induced in the material, that is ln of natural log of A original by A final. Okay, now for the material which is showing the strain hardening property, or during the process the strain hardening is going to happen on that material, then the sigma y will be replaced by the sigma y dash ln of A original by A final. And we know that this sigma y dash is nothing but what? For the strain hardening material, it is the average flow stress for that material. And how to calculate average flow stress? It is K epsilon to the power n divided by n plus 1. Okay, we have seen it in the basics of metal forming. So here the sigma d is equal to sigma y ln of A original by A final. Now see here, when I want to have the maximum possible deformation into the given material, so what can be the condition for that? See, when I am talking about the maximum possible reduction into the given material, then what I want actually, that whatever the yield strength of the material, on that same yield strength, if the material is deforming, that is we can able to draw that material at its yield strength only, then this will be the ideal case actually, where the sigma d and the sigma y are same. ओके, कि मटेरियल की यील्ड स्ट्रेंथ ही क्या हो रहा है? ड्राइंग स्ट्रेस है, मतलब मिनिमम स्ट्रेंथ, यील्ड स्ट्रेंथ इज द मिनिमम स्ट्रेंथ वेयर द प्लास्टिक डिफॉर्मेशन इज गोइंग टू स्टार्ट. सो एट दैट यील्ड स्ट्रेंथ ओनली वी आर गेटिंग द ड्राइंग स्ट्रेस, मीन्स we can able to have the maximum possible reduction. So suppose in this formula, say if I write here to get the maximum possible reduction, this sigma d is equal to sigma y, then tell me what is left here. This sigma d sigma y get cancelled, so 1 is equal to ln of A original upon A final, isn't it? Now same thing I am proceeding further. So what I will get? So e to the power 1 is equal to A original by A final after taking the antilogs of the both sides, or I will get 1 upon E is equal to A final divided by A original. So star mark this equation, and we know that what is the formula for maximum possible reduction, how to calculate that. So maximum possible reduction we can calculate as original area minus final area divided by original area into 100. This is nothing but the degree of cold work, isn't it? So it is nothing but what? 1 minus A final divided by A original, isn't it? Into 100. Solve it. So if we solve this, 1 minus, what is A final by A original? It is 1 upon E. 1 minus 1 upon E into 100. Please solve this. So 1 divided by answer, 1 minus answer. So nearly it is 63%. Okay. So if you solve this, you will get this maximum possible the reduction in the wire drawing operation. For which case? The ideal case of deformation, you will get the maximum possible reduction is up to 63%. Please remember. So here we get this. So many times they are asking this question also. So for ideal case, what will be the maximum possible reduction in the wire drawing case? Now we have come up to we know that the drawing stress we can calculate as sigma d is equal to sigma y ln of A original by A final. We know this. Now if we want to have the force or load in the wire drawing operation, so what is force? Force is nothing but the drawing stress into area. Okay, which area? See here, which stress is responsible actually to get this deformation done? It is the tension or the pull at the end of this wire, isn't it? Or pull. So here, this final cross-sectional area we are going to take for the load calculation. So area at the final stage. Okay, final stage. And which cross-sectional area? So I can write this force in the drawing operation as this sigma d into pi by 4 into d final square newtons. This is the force in the wire drawing operation. ये वाला diameter अपने को लेना है. This diameter we are going to pull and we are going to coil this drawn wire onto the power reels. Okay. So this is the force. If anybody asks you what is the power in wire drawing, how to calculate power? We know that power is equal to this force into velocity. Force in Newton and velocity in meter per second. So it will be the energy per unit time, which is nothing but power in watt. You will get, if you multiply this force by the drawing speed or velocity, you will get the power in the wire drawing operation. So this is how we can able to calculate the drawing stress, then the force, and lastly the power. So we have seen this is the ideal case of deformation. Let us take the second case, that is by considering the friction and redundant work. The second case we are going to take by considering friction and redundant work. Okay, so for this, how to give the formula for sigma d? So sigma d is equal to sigma y into bracket 1 plus b upon b into 1 minus A final divided by A original to the power b. Okay, so here the back pull and front pull we are not going to consider. So definitely there is one more term we are not going to consider. If given, you can take that back stress or front stress. The back stress, if the back pull is given, then the sigma b into again AF by A naught to the power b. We have to add that. But no any need, you just keep this formula in the mind, where what is this b? B is a constant, say it is equal to mu cot alpha. Alpha is what? Half the diangle, and mu is what? Coefficient of friction at the interface of the die and workpiece. AF is your final cross section of the wire, and A original is the original cross section of the rod, that is pi by 4 d final square, here pi by 4 d original square. You can replace this A final by A original as, you can also write sigma d is equal to sigma y into bracket 1 plus b upon b into bracket 1 minus d final divided by d original to the power 2b, like that you can also able to write. So sigma y is nothing but the yield strength of the material, okay, b is nothing but mu cot alpha. Once you get the drawing stress, now very easy to calculate force. As usual, force is equal to this drawing stress into final cross sectional area, which is equal to sigma d you got from this equation, and A final is pi by 4 into d final square times Newton. So this is how the force, when we consider there is a friction, and we also take into account the non-homogeneous work or the redundant work. Okay, so this is for the second case, friction and redundant work. Now again, even we can have this total drawing stress in the this drawing operation, wire drawing operation, when the friction is considerably large. Okay, so in that case we can get this sigma d, we get this sigma T actually, that is total drawing stress. Sigma D is a drawing stress. Now I am getting the sigma T is equal to, it's sigma y plus, it is into bracket sigma D minus sigma y into e to the power minus 2 mu L divided by this R final. Okay, so this is the formula to get the total drawing stress in the wire drawing process, where sigma y is the yield strength of the material, sigma d is the drawing stress that we have calculated from which formula, sigma d is equal to sigma y into bracket 1 plus b upon b into 1 minus A final divided by A original to the power b, where L is the die land, okay, and this is the die land, length of the deformation zone, and RF is the final radius of the wire. Mu is the coefficient of friction, okay. And what is the total load now? If they ask the total load, then this will be sigma T into A final. It is in Newton. So this is also the case, just keep it in mind, the formula. Okay, so no one going to ask you in GATE examination how these all come. You just have for the this deformation or metal forming processes, just the important formulas. Okay, no one going to ask the how this come. We can derive it, no any big issue. But for the GATE, as far as GATE preparation is concerned, there is no need for these derivations for the formulas. Okay, so students, we have seen the drawing stress for ideal case, we have seen the drawing stress for the friction and redundant, and also we have seen the total drawing stress and respective force calculation part. Okay, so let us take one example on whatever we learn now. Take this example. So see students, we have the question now on this wire drawing. What the question says: in wire drawing operation, the following data is given. The data is initial wire diameter 6 mm, okay, final wire diameter 5.2 mm, the die angle 18 degree, die land 4 mm, mu 0.15, yield strength of the material 260 megapascal. So they are asking the drawing stress, that is sigma d, and the total drawing load, that is the total. You have to consider the total drawing stress into the area. Okay, so let us see. D initial is 6 millimeter, D final is 5.2 millimeter, the 2 alpha value is full the triangle 18 degrees, so alpha is 9 degree, alpha is 9 degree, then capital B value is mu cot alpha. Here friction is given as 0.15, so tell me B is equal to 0.15 of cot of 9 degree or 0.15 divided by tan of 9 degree. So how much B? We'll calculate 0.15 divided by tan of 9 degree. So it is 0.947, 0.95 will take. Okay, this is our B value. Yield strength of the material is 260 megapascal and capital EL is equal to die land 4 millimeter. This is given. Okay, now see here, we have to calculate first the sigma D, drawing stress they are asking. So we know that for friction and redundant work, what is sigma D is equal to sigma Y into 1 plus B divided by B, okay, into bracket 1 minus A original by A final, or you can write it as D final divided by D original to the power 2 times B. No any back pull is given, so this is enough formula. Okay, so sigma Y is how much? 260 into bracket 1 plus B is how much? 0.95 divided by 0.95 into bracket 1 minus D final is 5.2 divided by 6 to the power 2 into 0.95. Simplify this and tell me the answer. So this product will be 1.9. So 5.2 divided by 6 raised to 1.9. 1 minus answer into 1.95 divided by 0.95 into 260. So it is sigma D, you are getting 127 megapascal. Okay, so first thing we got here, the sigma D is how much? 127 megapascal. That is the drawing stress we are getting for this. Okay, it is 127 megapascal. Now see, when we are finding out the total drawing load, we require first sigma T, which is equal to sigma Y plus sigma D minus sigma Y into e to the power minus 2 mu L divided by R final. So calculate the total drawing stress. Sigma Y is how much? 260 plus sigma D 127 minus 260 into e to the power minus 2 into 0.15 into die land 4 divided by R final, 5.2 divided by 2, that is 2.6, isn't it? Okay, so solve this. So this is 2 into 0.15 into 4 divided by 2.6 into minus 1. Shift e to the power answer 0.63 into 127 minus 260, it will minus 83. Okay, so 260 plus answer, it is 176.16. Sigma T will be 176.16 megapascal. Okay, so this is the value for the total stress. And once you get this total stress, what is total load? Total load we know, that is sigma T into pi by 4 D final square. Sigma T is 176.16 16 into pi by 4 into 5.2 square. So 5.2 square into pi divided by 4 into 176.16. So it is 3.74 kilonewton. 3.74 kilonewton. This is the F total, or load, total drawing load we have calculated like this. And the drawing stress, this is the drawing stress we have calculated. Okay.